All right. Okay. All right, guys. Welcome to today's workshop on transfer learning. We're Data Science Student Society. I am Peter, the director of workshop, and this is Tanveer. He's my machine learning lead. And our team is dedicated to host weekly workshop on various data science and machine learning topics. With heavily focused on applying these principles into practices. And DS3 also have projects, events, and online committees, and some other committees. We'll start recruitment early next quarter. So if you guys are interested, make sure to like us on Facebook and stay up to date with our any informations. So next slide, please. And today we'll have covered three major topics. The first one, we'll do a quick introduction on neural networks and what is transfer learning. And then we'll go deep into transfer learning in terms of computer vision and natural language processing. In each of those topics, we'll go through the basis and some common architectures like algorithms, and then we'll do a in-depth demo on each of those topics. And let's begin with neural networks. So I'm going to assume that most people have some understanding of machine learning. And what you're seeing right now is this graph is a single layer perceptron. It's one of the easiest and most simple neural networks. And you might have already realized this looks kind of similar to linear regression. But what's different is this step function, or also known as the activation function, that it gives the non-linearity using functions such as like there is 10H, there is ReLU, there is sigmoid, which is probably very similar to like logistic, also using logistic regression. So yeah, you get one constant and multiple n inputs, and each of those inputs have a weight, and in the end you do a weighted sum, and that go through. So before the step function is just linear regression, but it goes through the step function and it becomes nonlinear, and we'll call it like a neural network. So basically, that's the basis. Next slide, please. So what is transfer learning? The intuition is to use a machine learning model that has been pre-trained by someone else's on a very different or on a different but related task. And the reason why we're doing this is we want to reduce the labeled data needs. So let me give you an example. So I've worked on a personal project, and I tried to build a model to identify and detect license plate. But this is like a really niche area, so there aren't many labeled data sets on this. So what I used Google's pre-trained model that's already able to identify daily objects, and I used that to do this transfer learning to retrain it on this. I have some data on license plate. This is like you're standing on the shoulders of giants, right? You're already, for example, you're teaching a 6-year-old to identify cars instead of you training from scratch, because it takes a lot of computation power, takes a lot of time, and what Google and other pre-built packages or models, what they have done is they train it on really large GPU cluster, so it made it really easy for you to direct it to your own needs. So yeah, and this is I guess representation of the idea of transfer learning. On the left side, you have for example this ImageNet. It's one of the CV networks, and they also have a bunch of labeled images. So you have a bunch of data, and they train it on the same model, and it also have a bunch of labels. You can kind of see it like this. And on the right hand, it's the same model, but you can give it to a smaller data set, and it's gonna also perform well because it's already got this gist of what each picture looks like or each object look like. So if they get this, okay, maybe cat looks like this and dogs look like that. So they have this idea already. Next slide, please. So yeah, why we use transfer learning, and it's the areas we can use it for is it works pretty well for text and image related tasks, and it's better if the objective is a subset of the pre-trained model. Just like the example I gave before, license plates being I guess one of the daily objects, or or just like dogs and a lot of like animals. So if the model can identify animals, then it's definitely gonna be able to identify dogs and cats. So next one. And let me know if you guys have any question. I'm just going really fast here. So yeah, right now let's talk about the convolutional neural network. So this is in the realm of computer vision, and let me give you the essence. It is just to find features automatically. And originally, you would probably think, okay, maybe I'll just like, image data are just like 2D arrays. If we just lay them out one by one, like into a really long list, it's probably gonna work. But in reality, that image data is kind of different because, for example, if you see the image here, you can see that 4 is very close to 1, but on the right hand it's kind of far away. But in some cases, what's like close to, for example, your eye, like your eyebrow, it's very close. But then if you lay it out like a 1D array, it's gonna be very far away from each other. So yeah, like it says here, pixels have more in common with closer pixels, and laying them out here would lose some information. So next one, please. So they developed something called the convolution layer, and it uses this this kernel. What it is basically like matrix factorization on a sliding window. So you can see the GIF on the right. It's basically I think usually it's a square, and this is like Photoshop. You do a sliding window on each of those iterations, and do multiplication on the corresponding, I guess, pixels. So on you can see right here, it calculates what is this, 1 0 1 0. Yeah. So if the pixel is 1 and it multiplies by 1, it's going to be 1, and if it's 0, it's going to be 0. And eventually, you add up all the sum of the 9 pixels into on the right. So it says the convolved feature, and you can see it's a little bit smaller because that's how it is. Convolution layer kind of would decrease the size a little bit, but there are some measures you can do to prevent it from becoming smaller and smaller. Next one, please. So yeah, that was one very common layer, and this layer is, I'm gonna tell you guys, is called the pooling layer. So the reason why we use pooling layer is we want to make image smaller without losing too much information. So given a 1080p image, is just too large. There's so much details, and it's not going to be very efficient. It will take so much longer to train if you do it uncompressed. So what this layer does, as you can see here, it's going to divide the square, or the pictures, into multiple, I guess, non-overlapping parts, and for each part, it's gonna either, you can, the option to choose like max of the the 4 numbers on the each, I guess you can call it zones, or you can simply take the average, and you wouldn't lose too much information because this like maximum and average would kind of sum up this like be very representative of each zones, and eventually you'll get a smaller image without losing too much info. Yeah, and let me hand it over to Tanveer. He's going to talk about some architecture and demos.
Yeah, so what we just talked about basically is kind of like the basic ideas of how a convolutional neural network works. And what researchers have done over the last couple of years is they've basically taken those ideas and kind of fleshed them out to create much more complex architectures using those kind of pooling and convolution operations. So some of the most like at least industry standard like models used for computer vision right now are DS3, which are ResNet, which is developed by Microsoft Research, VGG, which is developed by Oxford, and Inception, which is designed by Google. And they all have their own pros and cons, but as of right now, for just like basic image classification tasks or image detection, these are like kind of like the 3 state-of-the-art models currently. So the idea of how ResNet kind of works is Peter just kind of talked about how in convolutional neural networks, we have these layers and each layer computes an operation and then passes on to the next. So what ResNet does here is it tries to basically allow each layer to kind of retain more information. And this uses these residual connections, also known as like identity blocks or skip connections. So on the right here with this diagram, you see we have these 2 convolution operations. So they take in this input image X. So it runs it through 2 convolution operations. And then at the very end, this outputs like the processed image features from convolution. And then before passing it on to more convolution operations below, what'll happen is we'll actually take the image before these convolution operations, concatenate them with the process features, so that way the next convolution operations are not only going to process the process features, but they're also going to process the original image before processing as well. So basically, this counteracts any loss in information, because when we do convolution, when we do pooling, these sorts of operations, we do tend to lose some information. But this basically allows the model to better retain information through the entire process. And then this also, this sort of like connection also solved like a very famous problem in machine learning called the vanishing gradient problem, which you can also like read more about separately. And then this is the model Inception, which is created by Google. So basically the idea of the methodology behind Google designing this sort of model was that there the convolution was a very, very active area of research where people didn't really know like what was the best like practice or methods for doing convolution. Like what were the best kernel sizes to use, what were the best like other parameters you'd want to use in convolution. So what Google did was, instead of trying to basically select like just one optimal like parameter for convolution, they basically created these things called inception blocks, which are kind of like the building blocks of the inception model. So what it does is it will basically run your input image through 1x1 convolutions, 3x3 convolutions, 5x5 convolutions, and then there's also other 1x1 convolution with pooling. And then what it'll do is at the very end, it'll concatenate all these process features together and then pass it on to the next inception block. And obviously, because we're doing so many convolutions, as you can kind of see like what the kind of like the finished model architecture looks like on the left here, like this is a really, really expensive computation. So Inception, I think out of the 3 models I just mentioned, is definitely like the most is definitely the most computationally expensive one to run because of just the sheer size of it, but it does result in some pretty good accuracy. So this model is really good only if you like have the computing power to also like keep training it. But obviously just note that prediction does run faster than training. So if you're like not trying to train this model and just use it out of the box, like that runtime isn't too bad to use. So we'll also talk about how you guys then can actually use a pre-trained model to basically work on a new task. So the idea is if you took this model Inception, right? So Inception takes an input image here and passes it through all of these convolutional layers. And at the very end, it's going to then output the prediction. And it outputs the prediction using just a simple like densely connected neural network layer. So the idea is we would basically cut the model off here. And what would happen is we use Inception as kind of like a feature engineering pipeline where what Inception does is it actually extracts features from our image, and then we train just like a really, really basic neural net that will just learn how to use those features to then work on our own task. So that's kind of what this diagram represents. So if we have Inception trained on ImageNet, which is like the standard data set for image classification, you would train it on this generic data set and then, for this generic task. And this is what this is representative of the model architecture. So we've cut it off here And A prime is just used to extract features from the image. And then we train densely connected layers at the very end that will just learn how to only use those features to then like basically do the task that we want. And I'll kind of also explain this more in the demo because I think it's much easier to see in the demo than just from these diagrams as well. So I'll kind of run through like a basic demo of how you'd possibly use transfer learning using the library Keras. So I can also post this in the chat really quickly if you also want to look at the source code on your separately. But the idea is here. So we're at the top here. We're just going to import a couple of different things, like just some data science packages and also the data set itself. So we're going to be using the CIFAR10 data set, which is basically image classification for 10 different types of classes. Basically, so the images kind of look like this. So we have like images of trucks, horses, birds, cars. They're kind of blurry just because of how like low dimensional, like low resolution they are. They're only 32 by 32 pixels, but of course they are images that contain information. So yeah, so basically we want to train a model that will take in these images and then, classify them. So what we're using here is we're using a library, a deep learning framework called TensorFlow. And on top of TensorFlow, there's a API called Keras that Google has created, where you can develop and define models in like pretty few lines of code. Like this is an entire neural network, a convolutional neural network designed like almost in like 10 lines. So we'll define our model and compile it here, defining like learning rate and loss functions. And if you want to learn more about that stuff, you can look at our deep learning workshop as well. But then here, this function is now going to fit the actually train the model on 5 epochs, where it's going to run through the entire data set 5 times. So we just kind of take a look at like what the training process looks like, and you have this like output here. But while that's running, then we can also kind of talk about the difference. So this is basically a basic convolutional neural network I just like quickly designed. But this right here is a model that we want to use using a pre-trained VGG16 model, the one that we talked about, like that was developed by Oxford. So we basically just defined that we want to use VGG16. We also don't want to train. We don't want to basically retrain VGG16. We want to take like this pre-trained model by researchers, and we don't want to change it or anything from our training process. We just want to use it as a simple feature extraction method, right? And then these dense layers right here, these 2 dense layers, are actually what we want to train. So we want these dense layers to learn how to use these extracted features to then output a final prediction for this new task that's separate from like the original ImageNet task. So that's kind of like how this differs. So here we're training literally all these convolutional layers and the dense layers. Here we're only training the dense layers. Honestly, I'll just let this finish at this point. We're like this far through. Might as well just let it finish. It should take like 30 more seconds maybe. But like, do you guys have any like questions so far? I know it's just 2 of us, but yeah, feel free to ask any questions, unmute your mic or type in chat. All right.
How large is the data set?
This data set, it's pretty large. It's like 50,000 images. It was taking way too long to train on the entire data set, so I'm only right now training on the first 10,000 images.
I see, yeah.
Yeah. So even with the first 10,000 images, it still takes a little while, but it still demonstrates the point.
Mm-hmm.
So yeah, this is kind of how the model looked like after training. Accuracy was going up. It was minimizing loss, which is kind of exactly what we want. And about a 49% training accuracy. Now let's look at VG16, where now we're only training these 2 layers. and we're not training anything from the convolution algorithm. Yeah, so I mean, as of right now already, after the first epoch of training from just the baseline model, the baseline model was only doing 22% accuracy after one epoch. We're not even done with the first epoch yet. We're almost at 30% accuracy. So you can already kind of see the difference here, where what a lot of machine learning practitioners like to do is they want to, as much as they can, they want to minimize whenever they train their own models from scratch, because that is a lot of work. That's a lot of computing power. That's a lot of time. It's always much easier to just use someone else's pre-trained work, so that way you save yourself a lot of effort. So that's what this is for. And also you can typically get better performance from using someone else's work than training your own from scratch. So like at the very end of the training process of just 5 epochs, right, we're at 50% accuracy. In like almost half the time, we're pretty much at that accuracy already. So you can kind of see that. But yeah, any questions about the code? Otherwise, I think I can just kind of let this run in the background and we can kind of move on. Yeah, but also if you guys want to learn more about like, all this code and what it does, I definitely recommend looking into the TensorFlow Keras docs. Like TensorFlow, like Keras specifically, the API built on TensorFlow is pretty beginner friendly. So it's pretty easy to learn about it. All right. So you can take this one, Peter.
Cool. So with computer vision talk about, we're going to talk about natural language processing. So there's a few approaches, usually people taking this natural language processing task. The first one is probably the most simplest. It's called bag of words. And just like the name, it's basically you're throwing a bunch of words into this, features using what they call like one hot encoded popular words. For example, you would choose the most popular 3,000 words, unique words, and then just basically you have 3,000 columns. For each column, you will count how many times it appears in one sentences of each rows or each document, and that's the most naive way to do it. And another way is the n-gram and skipgram. So let's give an example. So if you have a sentence, I love data science student society. If you're doing bigram, it would have multiple different features. The first feature being I and love. So this is how many times I love appear in the sentence. And then the second column would just be love data and how many times this appears in this sentence, and then so on and so forth. Also, there's trigrams, and as you already get this idea, it's gonna be 3 words per each column, and usually though it would increase, the accuracy of the model would increase until a point and then slowly decreasing, because sometimes you're like in English, for example, like I like to, or there's a certain phrase that sometimes appears more often than others. But once this sentence, the length of the sentence increase, you're not gonna get much occurrences elsewhere. So yeah, make sure you choose the right end for the n-grams. And lastly is what we're going to talk about majority of the time today is what they call word embeddings. So some of the common ones are word to vect. There's also dog to vect, glove, probably Tanveer's favorite. There's also Elmo and other stuff. So what this is basically they are like you can see below, high quality word embeddings, and that can be learned efficiently in a low space and time complexity. So going back to the example I gave before for the backforwards, if you have 3,000 columns, it's going to be really sparse, because not all the words is going to appear in like a document or a sentence. But what this word embeddings try to tackle is, for example, you want to, before I used BERT, which is Google's model. Oh yeah. Okay. Okay. Let me just finish that example. So you can specify how long you want the embedding to be, and then it will go through this BERT model and then give you, for example, 256 long embedding, and it's going to be very short compared to the 3000 if we were going to do back and forwards, but it still is very representative of the sentence. So yeah, in this slide, word embedding is for computers to process text, and we can't really have a computer to simply look at text. It has to have like some numeric representation, just like computer vision. And yeah, so words that have similar meanings would also have similar embeddings. So for example, if you do boy minus girl, will roughly equal to the distance between man minus woman, assuming that they are all represented in this high dimensional word embeddings. And this is Tanveer, he's showing an example. This is word to vect.
Yeah, so anyone just give me like a word, and you can kind of like see like in the word embedding space, like what are the most similar words. So maybe if we type like computer, right? I'm trying to figure out how you actually get like the most similar words. There's a way to do that in here though. Yeah, here we go. So basically these are the most similar words to computer. So you can see programming is pretty similar to computer in this high dimensional space. Desktop, Microsoft, electronics. So basically these like vectors that each represent each word actually capture the meaning of the word pretty well. And then, closely related words are also going to have like high cosine similarity, or like a small Euclidean distances in this dimensional space, which are like really, really useful properties of these things.
Right. This is a good visualization. Thank you for bringing this up. Yeah. So, yeah. So that's that. If you guys want to look more into this, you can go to the link project.tensorflow.org, and on the right side, similar to what he showed before, words or sentences that have similar meaning will be closer together in this high dimensional space.
Yep. So now we'll talk about, once we actually have like a way that we picked out a way that we want to actually represent the words, we then actually have to then figure out the model we want to use for like the machine learning task. So recurrent neural networks are kind of like the baseline deep learning approach for doing natural language processing. So the problem with just basic neural networks, right, is that once you actually have defined a neural network, it can only process like fixed length inputs. So like if you had a convolutional neural network, right, and you're only trained it to only work on 28 by 28 images, it can only work on 28 by 28 inputs. It can't work on like, different length or different size images. So recurrent neural networks basically kind of solve that, where for example, with sentences, right? Sentences can be of many different lengths. Like you could have like a 2-word sentence like good morning, or I love data science, 4 words, right? These are different lengths, and we want our model to be able to process both in the same way. So the idea is we basically would want to use any word representation from these from earlier with these RNNs, but obviously pre-trained word embeddings work the best and typically will always get better performance than just training your own word embeddings or using bag of words or anything like that. And recurrent neural networks, what's also useful about them is that you can also basically, if you are like savvy enough with PyTorch or like TensorFlow, you can kind of customize the architecture of these recurrent neural networks to solve many different tasks. So a one-to-one network is basically just like, it's just a normal neural network where it just maps one input to one output. One-to-many could be like basically you maybe input like an image or something, right? And then you want to output a caption. So you encode the image and then you output a caption to that image. So that's an example of that. Many to one would be like some sort of like text classification task, which is actually what we talk about. Well, the demo will be about later, where we input like a sentence and we want to classify like, is this a positive or negative sentence? Is this a positive or negative like review or something like that? Many to many is basically like you want to input a sentence, and then you also want to maybe output a sentence. So it could be useful for doing question answering, where you input a question and then you want your model to answer that question. Or it could also be used for like translating sentences between languages. So if you input a sentence in English, you output a sentence in French. And then many to many can be used for things like part of speech tagging, where you input a sentence one at a time, right? And then you label each like word as like a different part of speech. Or maybe you also want to like identify like named entities within that sentence. Like that's just some examples of like how you'd use some of these architectures for different tasks. Now, some of the problems with RNNs, which is why they're not like, you don't see a lot of researchers using RNNs for a lot of the state-of-the-art work these days, is that these the computations on the RNNs are a little too simple for the nature of like deep learning. So what'll happen is we'll encounter these like vanishing exploding gradient problems where we'll have like too drastic or too slow of weight changes, and like this basically very drastically slows our training process down, or even just halts it completely to the point where we're not really making any meaningful changes in our model or in our model weights. So the best way to kind of avoid this, if you still want to use like the RNN type structure, is you can use gated recurrent units, which kind of just add like some extra computations to avoid these problems, or you can use long short-term memory modules, LSTMs. And you can, just like how we talked about, where you can customize architectures with the RNNs, you can customize those exact same architectures with these two models as well. And another problem with RNNs is that you technically have to process each word sequentially or one at a time, right? So in your CS classes, you know this to be like O of n, where you guys are kind of just processing each word at a time, and it scales with O of n complexity. So to kind of solve this, researchers have created transformers, which are now like the most like state-of-the-art models that people are using. So transformers are a new type of model that have been developed in the last 2 years or so. And they were mainly used for NLP tasks, but now researchers are branching out to use them for like processing video, processing images. So don't be surprised if you guys see transformers popping up in other like areas of machine learning. But the thing that's great about transformers is that they actually compute the entire inputs like in parallel all at once. So this kind of like this speeds up prediction pretty greatly, because now instead of processing one word at a time, you actually process them all at once in parallel. And the key feature of a transformer that makes it so much better than a recurrent neural network at doing these NLP tasks is that you use an operation called a multi-headed self-attention, where what'll happen is so this right here is an example of like a sentence in French, right? So you have the word embedding for each of these words, and then you feed it into self-attention. And what self-attention does is it basically figures out how closely related words in a sentence are to each other. So like the idea is, if you have like the phrase data science student society, right? Data, science, student, society, like all these 4 words on their own kind of mean nothing, right? But in the context of the sentence where they're all kind of like, together as a phrase, they mean a lot. So multi-headed self-attention is all about basically contextualizing phrases, so that way so that way these word embeddings don't just account for just the meaning of the word, but also the meaning of the word in that sentence, in that position of the sentence. So it encodes more information. So yeah, so obviously we talked about with computer vision, some of the like pre-trained architectures we could use there, and transformers also have their like pre-trained architectures. So the 2 most commonly used ones right now are BERT and GPT-3. So BERT, which stands for bidirectional representation transformer, has been developed and used by Google. So they actually, like, just last year, Google just finished incorporating BERT into literally all of their products. Like the search engine now uses BERT. I think Google Translate also uses BERT now. They kind of are using this for like everything. And I even know like people, for example, who work at Twitter. Twitter uses BERT for doing like tweet recommendations now. It's kind of like the state-of-the-art model and the most popular in the industry, and people are like using this model like everywhere. So yeah, so basically, if you also want to use BERT to do like some sort of NLP task for your projects, I highly recommend also you check out DistillBERT, which so BERT is on its own is a pretty large model. So if you want to deploy this to like a web app or a mobile app, right, with limited processing power, just the base BERT model might not be suitable for your needs. So DistillBERT is basically a smaller version of BERT that uses significantly less parameters and maybe has like maybe 1% less accuracy. So like the trade-off is like pretty significant. You have a lot less process, like it saves a lot more processing power, but also conserves like most of its performance. Now GPT-3 is another transformer model that was like, it's kind of been developed very recently, so it hasn't been used too much yet and adopted much yet, but it's been developed by OpenAI, and you can always use that too. So I'll kind of give a demo now about how you can use GPT-3 to, or not GPT-3, sorry, BERT to do like text classification. Yeah. So for this demo, we're going to be using this wrapper library called K-Train. So what K-Train is basically a wrapper for Curious that also like has all these like BERT models already like pre-implemented in there for you. So like it's really, really easy to get started with, really beginner friendly. The only problem is like it's really hard to customize. So if you want to do like something more specialized with BERT, I highly recommend you maybe use PyTorch or something else if you want to do more fancier things. But if you want to do like really, really basic like text classification or things like that with BERT, then highly recommend using K-Train. So for this problem, I kind of just had some kind of data where we have like headlines and we want to classify they're clickbait or not. So a label of 1 is basically saying that headline is a clickbait title, and 0 is a non-clickbait title. So what we'll do now is we'll split them into training and test sets, and we're going to be now calling a bunch of different functions from the K-Train API. So this will take our training and testing data and then pre-process them for the model. Then this next line over here is going to then define the model. So we want to use DistillBERT, and then we're going to use the pre-processed data that we got from this other function up here. So now that BERT's defined, we will then define something called learner object, which is pretty similar to, not similar. This is kind of these sorts of like functions and objects kind of like taken after another library called FastAI. But we'll basically define that. And then when we do call learner.fit over here, we will start actually training BERT on this data over here. So this training process takes like a really, really long time. So I'm just going to maybe like let it run for like a minute or two and then stop it. But yeah, this is at least you guys kind of get the idea of like how this code sort of works. But do you guys have any questions so far, maybe? Oh yeah, I'll also paste the link to the transformer demo as well in chat. So this is taking kind of a while to start up, and I don't really know why. Let me double check something really quickly. I think I'll maybe have to restart this. I don't know what's really happening with this. It's kind of just frozen. So let's restart and hope it's working. I was thinking that maybe, oh, yeah, I'm thinking what maybe happened was that this was also using my GPU, so my GPU just stalled, having two different models training on it.
Yeah, so if you guys are, trying to run models using this transfer learning, you should probably try to use Google Colab or some like online platform.
Yeah, that's also another thing.
How-
Like I have just a 1060 on like a 1060 GPU on my computer, and it still takes like a while. So like,
Yeah.
if you have like an online cluster, like this is a good way you guys could use Google Cloud if you're trying to train a model. Like, so it's I guess, I mean, like I've run this before, but it just kind of gets getting stuck. I just want to kind of show the training process, but it's pretty similar to what we saw with the CNN.
That's
So
okay. You can just like shut it down.
yeah, we can just, yeah, it's kind of lagging my entire computer now.
Yeah, with Zoom opening and stuff. So
yeah, maybe it's just because Zoom's open or something. It's not working now.
yeah.
But I mean, the code does work. So like if you wanted to maybe use some of this for your own stuff, you definitely could do that. But that's pretty much it from our end, I think. We also have like some of the blog posts and stuff that we referenced for making these slides and stuff. Highly recommend if you want to learn more about how BERT works, how transformers work, how transfer learning works. Go through some of these blog posts. These two blog posts in particular are kind of like considered like the gold standard for learning about BERT and transformers. They're actually better. It's actually, these blog posts are considered more educational than the original research papers that were published on these models. So highly recommend like going through those. But
can you share that link in the chat too so they can access it?
Yep, I'll do that as well. But basically that's it from us. So feel free to like stay around, ask us any questions. But if you have any other questions about any of machine learning, feel free to message me or Peter through Discord or connect us on LinkedIn. Like I'm going to be kind of busy with my own SDX project this weekend, but like I can definitely do my best to try and help. But yeah, thanks for coming, guys. As I said, we'll stick around for answering any questions. Yeah, if no one else is asking questions, then should we just end it then?
Yeah, we can just end it.
Do you want to end the recording, Siddharthi?
Yeah, I'll end it right now.
All right.